Thank you, everyone. So I have the difficult challenge of presenting you advanced concepts in the deep learning. Advanced is very subjective. So what I try to do is give you a mix of more, let's say, intermediate topics in deep learning and then a little bit more advanced, at least what I consider advanced. So we will start by reviewing some of the things that you saw yesterday with Pierre-Marc on CNNs, because that's really like the basis of what I'm going to present today. And then give you just a little bit more advanced stuff on optimization, because it's something that you're likely to see during the tutorials. Then I will talk about some of the main problems in medical imaging. So for example, classification, segmentation, and object detection and localization. And also with the main architectures that you're also likely to encounter. And then I'll finish off with some very specific topics, recent topics on deep learning. Okay, so moving on to CNNs. So as you saw yesterday, CNN is a very, very common architecture for most tasks in computer vision. And what's really interesting, in fact, is that a CNN is actually quite similar, at least in terms of architecture, to the human visual cortex, right? In the sense that we have, let me grab the pointer. In the sense that when the visual information signal goes to the back of the brain, to the visual cortex, then it's going to be sequentially, sorry, processed in different regions of the cortex from very simple things like edges and blobs to eventually being recognized as a whole object. Okay? So what's particular about CNNs from a more structural point of view? If we compare them to, let's say, multi-layer perceptrons, well, in multi-layer perceptrons, typically every neuron in a layer is connected to every neuron in the following layer, right? So the problem with that, as Pierre-Marc explained very well, is that for shallow architectures, it's fine. But as soon as you start increasing the number of layers, that will give a lot of parameters, right? And this will just not be possible to optimize, let alone fit in the memory, right? So with CNNs, we have local connectivity. So that means that every neuron in a layer is connected only to certain neurons in the previous layer, okay? And that connectivity is local spatially, right? And another thing, another trick, if you want to reduce the amount of parameters, is the fact that the parameters in the network, in the CNN, which are basically the convolution weights, okay, are shared at the different position. Okay, so the weights that you see on these connections will be the same weights as you see for connections at a slightly different, well, in fact, at every other region of the image. Okay, so this allows, obviously, to have much less parameters and then much deeper architectures. All right. So a concept that's very important is the concept of receptive field. Okay, that's something that we hear a lot. We're not quite sure what it means. Well, the receptive field of a neuron is actually very simple. So I'm going to look at the neuron in this third layer here, right? Or second hidden layer. Well, the receptive field of this neuron is the spatial region, okay, if you want, of the input, in this case of the image, which can have an impact on this neuron. Okay, so all the pixels here, which if they are modified, can potentially change the value of this neuron, okay? Obviously, as we increase the number of layers, okay, we can increase the receptive field. Okay? It is necessary to have, in certain problems, it's necessary to have a large receptive field. For example, if we do a diagnosis, let's say, of the brain, well, we don't want to consider only a small part of the brain, unless, I mean, that's reasonable to do. But we want to have a whole context. We want to see the whole brain, or at least a large portion of the brain, to know exactly how the different parts of the brain relate to one another, right? So we need a large receptive field to do that, so possibly we'll need several layers to achieve that. Okay, yesterday, at the end of the presentation of Pierre-Marc, you started seeing CNNs. You're probably already familiar with CNNs. So what is the typical architecture of a CNN? Well, it's basically composed of convolution layers, which are followed by activation functions, units, to inject non-linearity. Then you have some pooling, and at the very end, if you're doing classification, you typically have fully connected layers, okay? I'm gonna review very fast these ideas so that just everybody's on the same page. Okay, so what is a convolution? Well, basically, we have an image. We take the convolution filter and we slide it at every position of the image. And then we take the values of the image at that position, the values of the convolution filter, and then we do a dot product. Okay, it's as simple as that. Okay, two things that were not seen yesterday, which are very important, is the first concept is padding, and the second one is stride. Okay, something that's, when you do convolution, you will be asked, what is the padding, what is the stride? So the concept of padding is very simple. So if you look at the image on the left, where you have a 4x4 image and a 3x3 filter, so if you naively apply the convolution, you will notice that the result doesn't have the same size as your image. In fact, the size of the resulting or the filtered image, or what we call the feature map, is actually reduced by 2 in width and 2 in height, right? What's the problem? Well, the problem is simply because the convolution cannot be applied on the border, right? So we will lose information along the border of the image, which is proportional to the size of the convolution filter. So how can we remedy this? Well, it's very simple. We will just pad the image, either with 0 values, which is typically what is done, or we can simply, for example, mirror the image or recopy the values along the missing pixels. Okay. Stride is a little bit more harder to understand. I guess intuition is a little bit harder to understand. So the idea is, instead of in a typical convolution, you will move the convolution filter by 1 pixel, left, right, 1 pixel up, down, right, in order to cover every single position on the image. But you can also skip some pixels while you do the convolution. For example, if you do the convolution at a given pixel, instead of shifting by 1 pixel to the right, you will shift by 2 pixels or 3 pixels, etc., right? So what's the point of doing this? Well, the point of doing this is basically to reduce the number of features, right? Because if you, for example, if you have padding and you have a stride of 1, so basically you only shift by 1 pixel, then the resulting image will have the same size as the input image, okay? In many cases, this is what you want, but you can imagine that if you have several convolution layers, then at some point this will generate a lot of parameters, or I would say a lot of feature maps. These feature maps might not enter in memory, etc., right? Of course, if we increase the stride, let's say we have a stride of 2, then we will divide, okay, or reduce the size of the feature map proportional to the stride. Okay, so as you can see here, right, because we have a stride of 2, we will divide by 2 the size of the image in the feature map. Okay, and the concept of stride is very, very, very related to the concept of pooling. Okay, in fact, some pooling functions can be seen as convolution with a stride of 2. Okay, one thing that's really important, it might not be obvious to all of you, is that when we think of let's say a 2x2 convolution, okay, the representation that we see in our head is like this sort of like, okay, this sort of like 2x2 filter that we move along the image, okay? This is not exactly the case, because we have to remember that the image that we're filtering might have several channels, okay? Think of a color image. color image has typically 3 channels, R, G, and B, okay? So in fact, the convolution filter is not 2 by 2, okay? But it's a 3D, it's not a 2D image or filter, it's in fact a 3D tensor. Why? Because as you can see in the image here, okay, it will be a 2 by 2. Sorry, when I say 2 by 2, I mean 2-dimensional. Okay, forget what I said. So it will be 2-dimensional along the image, of course, because the image is 2-dimensional, but we also want to aggregate the values across the feature. Okay, so the filter will actually be a 3D tensor. Okay, if we're filtering a 3D volume, which is often the case in medical imaging, then the filter will be a 4D tensor. Okay, and what is the size of so what is the depth or the number of channels of the resulting feature map? Well, it's simply equal to the number of filters. Okay, so if you want to have a filtered image that has 1,000 channels, you will need to apply 1,000 such filters. Okay, so now you can start understanding how many parameters you need. Okay, because the convolution filters are tensors, and then you need as many as you want to have feature maps in the next layer. Okay, activation functions, again, this is a repeat from yesterday. I don't want to go too much in the details. Just to let you know that the two, I would say, most popular, at least standard functions that are used nowadays are ReLUs and leaky ReLUs. Okay, so the goal of ReLU is to eliminate the vanishing gradient problem of sigmoids. Okay, because in sigmoids, when you're either have very large positive or very large negative values, well, the derivative becomes 0, right? So in ReLU, you basically have 0 values. So if your input signal is negative, then it becomes 0. But if it's positive, then you will always have a gradient. Okay, so you will not have the vanishing gradient problem. However, one problem that you have with this is that if the neuron, for some reason, if the value previous to the activation function is negative, then the output will become 0, and we say that this neuron is non-activated, okay? And one of the problems that you might have is that the neuron might stay deactivated for the rest of optimization, okay? Which might be a problem. So we want to give the chance of the neuron to become activated again so that it can eventually have a function in the network. So what we typically do is we give a small gradient, having a small slope here in the negative side of the activation function. Okay, right, so as I said, pooling is very similar to convolutions with stride in the sense that we will, for example, do a convolution and then shift by a certain amount. But the difference is that instead of learning the convolution filters, we will apply some predefined operation which consists in aggregating the values in some way, right? And the two most, well, actually the most famous, most popular or most commonly used way of doing this is the max pooling, okay? So this is a max pooling with a stride of 2. It's a 2 by 2 max pooling. So what I do is I consider 2 by 2 regions in my image. I will take the max value, which will become the first value of my pooled image. And then instead of moving by 1, as I would do in a convolution, I will move by 2. So basically I have a stride of 2, so that the windows or the pooling windows will not overlap. Okay? Is that the only difference between pooling function and convolution function? Does anybody know another difference? So for example, if I look at average pooling, would average pooling be, I guess, equivalent or similar to some convolution where I simply divide or take the average, so the weights of the filter would be 1 over k, where k is the total number of elements in my filter.
The parameters of pooling is not learnable.
The parameters for pooling is not learnable, but okay, that's true. But there's another difference. There's another big difference. Anybody knows? Okay. The difference is that pooling is typically done per channel. Okay, remember when I talked about convolution, okay, I said that when I apply the convolution, I actually do a weighted sum of the values across channels. Okay, so I consider like this whole chunk. But when I do pooling, I would actually do pooling for this channel, and then for this channel, and then for this channel, etc., right? Okay, because it doesn't, imagine the channels represent very different things. It doesn't necessarily make sense to take the maximum of different things. Okay, that's another difference. All right. So going back to the receptive field, so I mentioned the problem that if you want to increase the receptive field, and in medical imaging, or as well as different problems, okay, as soon as we have very large images, or we have, let's say, images where the global context is important, we generally want to have a large receptive field, okay? Because we don't want the decisions to be too local, right? So, but how can we increase the receptive field of a convolution without increasing the number of parameters, right? It's kind of like a trade-off. Well, there's a very easy way of doing this, which is called a dilated convolution. Okay, what is a dilated convolution? Imagine you have a standard convolution. Okay, so the filter would be composed of elements in a grid, right? Well, instead of applying this filter directly to the image, what you do is you sort of inflate the filter in such a way that instead of having the filter elements being side by side, they now have gaps in between, okay? It's not super clear, but look at the, oops. So look at the dark blue elements on the lighter blue image, and these dark blue squares correspond to your filter. And you can see that there are holes in between, okay? And this is why dilated convolutions are often called à trous, okay? Of course, and there's a way to control how dilated your convolution is. There's a parameter called, for example, D. And of course, if you set this parameter to 1, then you basically have a standard convolution. Okay, is it clear for everyone so far? Yes, if you have any, yes?
What are the consequences of doing this kind of convolution?
Okay, it's a very good question. Well, the consequence is that you increase the receptive field. So as you can see, we consider a larger portion of the image. And you can imagine that if we inflate further and further, then eventually we could consider maybe the whole image. But the number of parameters remains the same. So the number of dark blue square, which are the parameters, is exactly the same as if I had a standard convolution. Okay?
Do you extract the same information? Do you lose some information?
You will lose some resolution. It's kind of like a sampling or, yes?
Sorry, but I don't get the difference between this and pooling and then convolution.
It's very different because when you do pooling, you consider, for example, if you do max pooling, you will consider the max value. In this case, there's no definition of max. It's just the way you sample your pixels when you do the... okay, I think I will just move on because I have a lot of content. And
okay, I think it's also better.
Yeah. There's a lot of goodies at the end of the talk, so I don't want to miss those. Okay, a little bit about optimization. Again, these are very, very, very important concepts. You will likely see those if you do deep learning. So going back to gradient descent. Okay, so what we do in gradient descent, so we basically compute a displacement. Okay, so we're going to modify the parameters using displacement. You can think of this displacement as a velocity, right? Which tells us this is where we are going next? Okay, and this displacement, of course, is computed as the gradient times some value eta, which controls the step size. Okay. There's a better way of doing things, which is to add momentum. Okay, the best way of seeing what momentum does is thinking of a hill, for example, like this, and having a ball rolling down the hill. Right? What's going to happen? What's going to happen is the ball is going to start moving slowly, but the further down it goes the hill, the more it will accelerate. Okay, and this is momentum. Okay, and then if at some point there is a bump, okay, the ball will have the capacity to jump over the bump because it has momentum. It will not just stop there. Okay. Whereas in gradient descent, it would go down, but then the gradient would suddenly shift in the opposite direction, and then we would stop. So what do we do with momentum, more precisely? Well, we still consider the gradient direction, but we take a mix of this direction and the previous change that we did to the weights. Okay, so now we have two parameters if we want. One which, well, we could also write it as one parameter, nevertheless. But one which controls how much of the previous movement or step do we consider, and how much of the gradient do we consider. Okay, so let me summarize what this does. Okay, so it will basically help accelerate learning when the gradient direction is stable. So if we constantly take the same direction, okay, in our optimization, it means that this is a good direction. Maybe I should take larger step size, right? Otherwise, I'm just wasting my time doing little steps like this. If I've been doing little steps like this for 1 kilometer, maybe I should start running in that direction. Okay, in the opposite scenario, if there's a lot of bumps, I don't want to go back and forth, as I mentioned in my example. Okay, I want to keep going the same direction because these bumps are not really important. So overall, optimizing with momentum gives a faster convergence, and this often leads also to a better solution, right? Because we don't get stuck in those local or bad local minimas. And one of the most famous methods that applies momentum to learning is ADAM. Okay, so ADAM is not an acronym, but it stands for Adaptive Momentum Estimation. Okay, so bear with me here. So it's actually quite simple. There are two things that we compute during the learning process. One is the average gradient. Okay, it's not the exact average, it's the decaying average, meaning that we give a greater importance to recent values that we have observed than older ones. Okay, and we also calculate the decaying average of the second moment of the gradient. Okay, which is basically the uncentered variance. So how much does the gradient vary from one step to another step? Okay, then there's this little thing, normalization, which is not super important to understand, where we will take these values and then divide them by something. What is that thing for? Well, you can see that the gamma values here, okay, these are parameters, and they're between 0 and 1, right? So when t is the number of iteration, when t goes to infinity, or as we have done sufficient number of iteration, this will become 0, and then the normalization will not do anything, okay? So in other words, the normalization is really only applied in the first iterations. And the reason why it's applied is because when you initialize your network parameters with typically zero mean Gaussian, which is the standard way of doing, there is a bias of the gradient, and there's a bias towards 0, okay? So what this does is in the first step of the optimization, it will kind of like make sure that the values are not too close to 0, okay? It will sort of artificially inflate the values to give it a chance to the optimization to actually move forward. And then as the process is already ongoing, then it will say, okay, I don't need this normalization anymore. I'll just let it run as it is and then compute the decaying average. Okay, so far so good. Okay, right, so we have the mean gradient, which is a way estimation of the momentum. And then what we do is very similar to the momentum idea that you saw on the previous slide. The only difference is that here we will divide this value by the square root of the variance, so by the standard deviation, right? Why do we do this? Because we want to basically reduce the step size if there's a large variance, okay? In other words, if we notice that the gradient is starting to vary, so meaning that the direction is not constant, that means that maybe we are going a little bit too fast. Okay, if we're going a little bit too fast, let's slow down. Okay, so it's a more adaptive way of using momentum. All right, so just to convince you, here's a plot that compares Adam with other, of course, I'm going to show you the one where Adam works best. Comparing Adam, which is in purple, with other momentum techniques, and you can see that in some situation, it's not always the case, and even for some problem, Adam is worse than just standard gradient descent. But in most cases, or in many cases, it really does a better job. Okay, and because it's adaptive, oftentimes you don't have to tune so much the learning parameters. Another very important concept is batch normalization. This is kind of like a misunderstood concept. Even there's been some researchers have criticized this because there's not so much theory behind it. But in practice, it works really, really well. Okay, so to explain this, we have to go back a little bit to the beginning of the, standard neural networks, where what we do is we typically take the input, okay, regardless what the input, of course, let's not look at images, let's just look at a vector of input. Then what we typically do is we will shift every input will be shifted so that the mean becomes 0 and such that the standard variation or variance becomes 1, okay? So why do we do this? Well, we do this basically because we want to have a uniform sort of a distribution of our input so that there's not one input that has a stronger signal to another input, okay? This is like a very, very standard technique in neural networks. People were using that long, long time ago. So then some people ask the question, well, why not do this? So why do this only in the beginning for the input and not do it over the whole network? So this is what batch normalization does. So for every, for the input of every single layer, okay, so the feature maps that are produced by the previous layer, we will apply this normalization, okay? So we will remove the mean, so we will remove the mean so that the new mean becomes 0, and then divide by the standard deviation. Okay, there's two little things that are super important to know. First thing is we don't do this for the whole training set, we only do it for batches. Okay, so a batch, if you remember, is a set, a small set, a mini batch is a small set of training example. Okay, Well, we will take this small set of examples, and then as we do the forward propagation, we will compute the output of the activation units. We will normalize these activation based on the batch mean and batch variance. And this is what we will pass on to the next layer. Okay. Another thing, which is, again, adds a little bit of complexity, is that if we do this very naively, there might be a problem because the weights in the next layer might not be optimal for this normalization. So what we do is we allow the network to rescale, to rescale the values, okay, and to shift these values. So we undo the shift and scale. So we have a mean of 0, a variance of 1. But then we let the network decide how to rescale and shift these values based on two parameters, gamma, which is the scale, and beta, which is the shift. Okay. The difference is that these values are learned. Okay, so batch normalization basically is a way of learning the different scaling at each layer. Okay, what is the goal of batch normalization? There are two goals. The main goal is stability. Okay, because we are doing normalization, okay, we make a given layer in the network less susceptible to the changes in previous layers. Okay, so imagine that in the previous layer there's changes going on in the parameters. Okay, so the signal might vary, right? It's normal because it's an ongoing optimization. Well, we don't want these changes to impact too much the following layers. So this is why we apply this normalization. It makes it more stable. Another thing is because we are calculating the mean and the variance on a mini batch basis, it injects a little bit of noise. Okay, in the same way that stochastic gradient descent will have noise because the gradient is not computed over the whole set of examples, but on individual examples or on a small batch of examples. Okay. Next concept is dropout. Okay, you probably have heard of dropout. So while we're doing training, okay, so imagine you have a standard network. While we are doing training, we will randomly drop some of the connections. So what does it mean, drop a connection? Well, basically, we assume that there is a 0 weight on this connection and that it will have no impact. So for example, if there was a connection from here to here, we're not dropping connections, we're dropping neurons. So we're basically disconnecting the neuron from the network, okay? So all the connections to and from these neurons will not exist anymore, okay? The reason why, so this is a regularization technique, meaning that we do this because we want to reduce overfitting, okay? The reason why this works, okay, is basically because if we do this random disconnection, so imagine you have a neuron and this neuron depends on a certain number of neurons before it, right? The neuron will sort of learn to not rely so much on specific neurons in the previous layer, okay? Because that neuron, so these neurons in the previous layer, might be disconnected at any time, right? So it will sort of distribute the information that it needs to do the prediction across the different neurons in the previous layer, okay? And then when we do this, it will favor simpler solutions, right? So we will not have so the connection weights will not be very high or very, very low. They will be a bit more uniform, right? Because we don't want to give too much importance to specific neurons. We want to be sort of a very safe in our estimation of which neuron is important for the prediction. Okay. Another very cool way of seeing dropout is to consider that if I take a network and I randomly disconnect some neurons, this gives me a new network. Okay. And then as I optimize, I will see many, many of such networks. So if you know what ensemble learning is basically training a set of models and then taking the average of the prediction of these different models. In a way, this is what it's doing, okay? Because when we are optimizing the loss function, we're not optimizing the loss function of a single model, but we're optimizing the loss function of an infinite number, or I mean not infinite, but a very large number of models, each of which is produced by randomly disconnecting some edges. Okay, so there's a very, very nice paper which connects dropout with stuff like Bayesian learning, for example. Okay, how do we choose the dropout probability P? Well, if you remember that dropout is a regularization, then typically what people do is they will pick larger or higher values of P for the layers that have more parameters. Okay? So in a classification network, most of the parameters are found in the fully connected layers, okay, because that's where we have dense connections. And so we will typically have larger p-values in these layers to avoid them from overfitting. Okay, so now I will start moving on to problems. Okay, starting with image classification, which is I guess, the basic problem, the problem that started, I would say, the revolution of deep learning. Okay, classification, we have an image, and we want to predict either one or multiple tags. Let's consider that we only have one class to predict per image. Typically, what we do is we predict a distribution over our classes. Okay, so we assign a probability to the different classes and then pick the one that has the highest probability. Okay, you probably know this. You've probably seen a similar slide in many, many presentations. But I think it's really relevant. What are the challenges? Well, I mean, if we see this image, it's a dog. I mean, a child, a 1-year-old, maybe 1 year and a half old, will know it's a dog. Can you explain why it's a dog? Well, I don't know, it's a dog. It's obvious. But the computer sees this, okay, a matrix of values. So the whole objective, the whole difficulty of computer vision research was to translate this into this, okay? But there are many, many other challenges, basically variations due to viewpoint, illumination, the scale of objects. The objects can be deformed, they could be occluded by other objects, etc. Okay, so in summary, image classification is very easy for humans. We do it every day, otherwise we would not be able to live. But it seems to be hard for computers. Or is it? I mean, that's the question. Is it really hard for computers? Well, one way of answering this question is we can look at one of the main challenges in computer vision, which is on the ImageNet. It's a large data set of image for classification and object localization. The 2017 version of this challenge, which was the last version, had over 1 million images and over 1,000 classes. Okay, so that's a lot of images, and more importantly, that's a lot of classes. Okay, it's not saying is it a cat or a dog, but now you have a lot of possibilities. Okay, and these are the results of the challenge. Okay, so from 2010, when it originally started, to the last edition of the challenge in 2017. And the blue line, the blue bars that you see are the top 5 error. Top 5 error means that if I get 5 choices, okay, so the question is what is the class of the object in that image? And I get 5 choices over 1,000 possibilities, okay, how many times will I be wrong? Or being wrong means that none of my choices are the correct one, okay? So in 2010, the top 5 error for the best method, the method that won the contest, was 28%. And now we're at 2.3%. Okay, how good are humans? 5%. Okay, of course, this is a challenge. This is, obviously the images have been sort of selected. There's only 1,000 categories, where in real life there's way, way more. But it goes to say that computers seem to be doing fairly well at this problem. So I'll give you a little bit of history on how this happened by showing you the different architectures that were proposed. Okay, so starting with the first architecture, which was proposed by Alex Krzyzewski and Jeffrey Hinton at the University of Toronto. You might have heard of it, AlexNet. So AlexNet, in today's standard, is a very, very simple architecture. It only has 8 layers. Okay, basically convolution pooling, etc. Okay, for 8 layers. But it completely blew the competition away. Okay, in fact, it had a 11% lower error than the runner-up of the challenge. I mean, that's a huge difference. 11%. We're not talking 1%, 2%, 11%. What's really, I mean, today, almost no one will use this architecture because it's very, very simple. But what's really interesting is that these guys came out of nowhere and they proposed most of the techniques that are actually still in use today, including ReLUs, data augmentation, dropout. They even use GPUs for training. I mean, today we cannot think of training a neural net without GPUs. Okay, the next year winner was ZFNet. It was sort of like a minor improvement over AlexNet, so I'm not going to go over the architecture so much. But what was very interesting about this work is that they proposed what is called a deconvnet, deconvolution net, that enabled them to see what is actually learned by the different convolution filters, different convolution operations across the network. Okay? And you could actually see, so this network was trained with ImageNet, and you could actually see that as you go deeper in the network, what the network learns is more and more complex object detectors, okay? Starting with edges, all the way down to faces, and you know, for example, if it's a car, you could actually recognize some parts of a car. Okay, next up is VGG. So VGG was proposed in 2014, okay? First thing that you can see is we went from 8 layers to 19 layers. Okay, already the deep learning trend is moving on. What's special about VGG? Nothing. It's very, very, very simple. In fact, it's way more simple than AlexNet was. Why? It only has 3 ingredients: convolution, which are 3 by 3 all the time. Okay, they don't have different convolution sizes. ReLUs and 2 by 2 max pooling. Okay, so how is it that using only these simple convolutions, you can achieve deeper architectures? Well, the idea is this. Okay, if you take a 3 by 3 convolution and you cascade another 3 by 3 convolution, okay, so imagine 3 by 3 convolution followed by another 3 by 3 convolution, what you get is potentially the same as a 5 by 5 convolution. You have the exact same receptive field as a 5 by 5 convolution, but you have much less parameters. Okay? In other words, what this architecture told us is like, there's no need to have huge convolution filters, okay, because they take a lot of parameters. And besides, we could model them as successive smaller convolutions, which globally will take less parameters. The next one, so the following year, wait, was it following year? Same year. Sorry, okay, so the winners that year was not VGG, but it was GoogleNet, or GoogleNet, as a reference to Lanet. This is what it looks like. Okay, wow. This is way more complicated. So let's try to break that down a little bit so that we can understand it. So there are these repeating blocks, which are called inception blocks, which are still used today in many architectures, or inception modules. Okay, we also have intermediate loss functions. So instead of having a loss function only at the end, we have, within the network, we have some other loss functions. And what is the goal of these loss functions? Is because if we only have a loss function here, then the gradient, when I do backpropagation, has to go all the way back. So by having these loss functions here and here, I actually allow gradient to flow from here and here. Okay, so it's sort of like injecting signal in the middle layers of my network. And we're going to see a little bit later that this is absolutely not necessary anymore. And lastly, they replaced the fully connected layers by pooling layers, but this is a detail. Okay, let's take a closer look at the Inception module. I mean, this is basically what is most interesting in this architecture. So let's say you want to implement a convolution layer, right? So you have a choice to make. So I said before that you can always take a smaller convolution and combine them, but let's suppose that there is a reason, and there actually is, but I don't want to go into the detail, that you might want to use larger convolution filters. Okay, so do you consider a 1 by 1 convolution? Do you consider a 3 by 3 convolution, 5 by 5, or do you consider max pooling, right? You have to make a choice. Well, maybe you don't have to make a choice. What you could do is you can basically compute all of these possible operations and then concatenate the output of each of these operations into a single vector or feature map, and then let the network decide which will be more useful, right? Again, we want to avoid as much as possible having the human make the decision. We want the network to learn what is the best decision. But the problem is if we do this, there will be a lot of parameters. Okay, because 5 by 5 convolution, again, takes a lot of parameters, and we have to do all of these. So what is the trick of Inception module? The trick is that we will add 1 by 1 convolutions before these operations, or in the case of max pooling, right after. Okay? This is to reduce the number of parameters and make the operations faster. Okay, why is that? Well, if you look at a one by one convolution, what it does, okay, it doesn't change the size of the feature map in terms of height and width, okay, because it's basically going 1 pixel at a time and just computing some values. Okay, so there's no stride, there's no border effect, there's nothing. What it does, in fact, it will simply take all the features for a specific pixel or channels, call it what you want, okay, and then we'll produce, so at the same location, we'll produce another feature map, another vector, which is proportional to the number of filters. Okay? So of course, if we choose a number of filters which is smaller than the feature size that we had initially, then we can reduce significantly. So we get something that has the same width and height, but the depth is much smaller. Okay? Another way of seeing this is that this operation is basically a learnable feature pooling. Okay? Like a feature selection or feature reduction. Okay? Let's say you have 1,000 features. Well, maybe a lot of them are not really useful, or maybe a lot of them are correlated in such a way that you can reduce them. And this is what you give to the next layer. Right? And these one-by-one convolution layers is what we call bottleneck layers, right? Because they squeeze the information, reduce the number of features. Okay, how efficient is that strategy? Okay, let's see. AlexNet, 8 layers, 72 million parameters. GoogleNet, 22 layers, 5 million parameters. Okay, so that's 12 times fewer parameters than AlexNet. Okay, this is amazing because now we are going much deeper, but we can also do it with less parameters. Okay? Okay, the next one is ResNet. So people started asking, okay, well, having deeper architecture seems to be good, right? So why don't we just increase the number of layers? And that's it. We'll solve the problem. Well, it turns out that if you do that, okay, not only will you overfit, so your testing error will increase, but you will also find out that the training error increases, okay? And this says that it's not an overfitting problem, it's a training problem. Okay, the limitation is that we just don't know how to train a network that is so deep. Okay, because you would assume that it would overfit, right? Because the network is so powerful. But in fact, no, it doesn't happen because there's many issues with training, for example, the vanishing gradient. So a very, very amazing solution that came in 2016 to this problem is ResNet. So what ResNet does, so instead of having like a simple direct feed-forward connection in your convolution, what you do is you do that, plus you will simply recopy the input at the output, and then you will take the sum of your transformation with the initial input, and this is what is the final product of your residual. Okay, this is called a residual block. So basically what you're doing is you're not learning the transformation itself, okay, but you are learning the residual that is required to have the transformation. Okay, you see what I mean? So if you have a feature map, you want to get to the next feature, instead of computing the transformation from here to here, you compute the delta, the difference. What do I need to add or subtract, basically? Okay, so in terms of advantage, it's really hard to explain how this works, but let me try to summarize from my perspective. So one possibility is that the residual requires less information to describe as the transformation itself, so we can possibly learn it better. Another thing is because we have these I guess, skip connections, you can call them, the gradient doesn't have to go through all these layers to come here. It can also take this connection when we do the backpropagation, and therefore, because of that, we can jump more quickly to the first layers and avoid the vanishing gradient problem. Okay, and because we are doing this, we can now have very, very deep architectures. I'm talking about over 100 layers deep. Okay, and lastly, so this is the paper that won Best Paper Award at CVPR 2016 or 17, is the DenseNet. So DenseNet is kind of like taking the ResNet idea, but pushing it to the limit, okay? So what do? Let's look at the dense block. So what the dense block does is it will add a skip connection, okay, so maybe I should not call it skip connection, it's not really that. So it will take the output of every single layer and make it as input to every one of the following layers, okay? And what I mean by making input, I mean concatenating. So basically, the input of the last layer is the output of the previous layer, as in a standard network, but also the output of this layer, and also the output of this layer, and also the input to the network, okay? So we're talking about very, 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 very large input to this last convolution layer, okay? Is it super complex to have this network? It seems like, wow, okay, this is crazy. You're basically, the input here is huge. But in fact, it's not so bad because we only need to compute these values only once. Okay, for example, the output of this layer, we compute it once and we store it. Then when we need to use it here, okay, it's already been computed, it's already been stored. We just have to, boom, feed it to the network. Okay, so this is it for image classification. So just to give you a little idea, I think there's been some examples presented before, but this is an image classification for medical imaging, where you basically have MR images, and what you want to predict is if the subject is healthy, if the subject has mild cognitive impairment, or the subject has Alzheimer's. Okay? It turns out that convolution networks work very well for this problem. Okay, so the next problem is semantic segmentation. Okay, so here the goal is not to classify an image, but to classify the different pixels in an image. Okay, we want to assign for every pixel a class. What are the main differences between classification? Well, the difference is that this is a dense problem, in the sense that we have to do as many predictions as there are pixels. So imagine if you have 1 million pixels, that's like solving 1 million classification problems. And also it's structured in the sense that the predictions are not independent. Okay, so there's no point in making a prediction here and then predicting the pixel on the side in a completely independent way. One possible way of solving segmentation with a network, with a classification network, okay, is taking the classification network. Let's say classification network is defined for a fixed size image, and then just moving this classification network over the image, and then just looking at the output for every pixel. Okay? Of course, if you do this, it's terribly inefficient, okay? Because you're going to do a lot of redundant operations. There's a lot of convolution operations that you will just do again and again. You could have done them only once. So a very simple idea, but that has, made a huge difference in computer vision, is this idea proposed by Long et al., where you can take a standard classification network and make it fully convolutional. Okay, what does that mean? It's basically you remove all the fully connected layers, because the fully connected layers are not convolutional layers, and you replace them by one by one convolutions. Okay? As you remember, one by one convolutions, they do not change the spatial size. okay? So in the end, the output that you get will be proportional to the input image. Okay, instead of having one value, well, you will have a mask of values that will be proportionally in size to the input image. The main problem here is that because of the max pooling operations, the output will be very, very coarse. Okay, you can see here that, yes, we do get a segmentation map, but it's not really interesting. We know that there's a cat here, but I mean, that looks very coarse. I mean, it doesn't look like a cat at all, at least from a segmentation point of view. So the trick is to take this very coarse map and to make it more detailed, okay, through some upsampling. And this is achieved by what we call transpose convolution. Okay, so it's kind of like the reverse of a convolution. How does it work? Well, if you consider a convolution as a matrix operation, okay, so this is a convolution, this is the same operation but defined as a matrix operation. Okay, you can see that the convolution filter weights are just shifted. Okay, it's a 1D convolution, by the way. That's why it might look different from what you've seen before. Well, a transpose convolution is very simple. You just take this filter matrix and you transpose it. Okay? That's it. So now you're actually upsampling, because here, if your input is a vector of 3 elements, if you apply this transpose matrix, then the output will be a vector of 5 elements. Okay, so you go from 3 to 5, you're actually upsampling. And cool thing is this transpose convolution is also fully learnable. Okay, so it's not just interpolation, it's basically a learnable upsampling. Okay, so I'm going to skip because I see time is running out, but so another way of, right, okay, so if we do this, sorry, so this is what we call the encoder-decoder architecture, right? So the upsampling occurs here. So this is, I guess, the network that you've seen before. This is the upsampling step, which is kind of like the opposite. If we do this, there's still a problem, is that we get there's a lot of spatial details, very fine details that are lost here, right? Because imagine you compress an image and then you decompress that image. Sure, what you get is an image of the same size with possibly some details, but there's a lot of information that would be lost in the compression step, right? So one way of remedying this is to add skip connections. So basically allowing that high resolution information in the first layers to be reused, okay, in the decoder, in that step here. And if you do this, you get a very, very famous architecture. If you do medical imaging, I'm sure you've heard of it. It's called the UNet. In fact, it's probably the most famous architecture for medical imaging, and it's the most cited McKay paper of all time. And it was proposed in 2015, okay? So very, very popular. There is a 3D image equivalent, so for volumetric data, called the VNet. Not much innovation here, but basically you go from 2D images to 3D images. And last thing for segmentation is in medical imaging, we often have multimodal data, right? So let's say you do brain segmentation. You will have T1, but you could also have T2, you could also have FLAIR, etc., right? So how do we consider these different image modalities into the network? Well, one very simple possibility is, okay, assuming that the images are all scaled to have the same size, then we can just stack them as different channels in our input. This is what we call early fusion. Okay, option number one. Option number two is, okay, let's process all these modalities separately in different, if you want, convolution networks. And then when we have the final convolution features, we can just aggregate them. And this is what we use for the upscaling and I guess segmentation part. Okay, this is what we call late fusion. A third option was proposed in the hyperdense hyperdense network. Is a little bit like the dense network. Is to say, let's say we have two different modalities. So sorry, the drawing is a little bit messy, but the idea is very simple. Let's say you have two modalities. You will have two branches, one for each modality. You will have dense connection in each of these branches, like a dense net. But you will also have dense connection across the different modalities. And what this does, it allows a network to decide at which point it's best to share information from one modality to the other. Okay? And it turns out that the patterns of connection that we observe is similar from one data set to another. So let's say we do it on one brain segmentation data set. We observe some pattern. For example, we see a high connection between this layer and that layer from T1 to T2. And then we do it in another brain segmentation data set. Well, we get similar patterns. So which means that actually it sort of makes sense to do that. And it's good that the network has discovered that relationship.
Sorry. Time is running, and I think we will have time after the break to continue these presentations.
Oh, yeah.
Okay, so I don't want to stop you earlier, but I'm sure there is a lot of questions from the first part, so the dropout, batch normalization, and so on. And of course also on the important techniques for classification and segmentation. So I prefer to stop here now, ask some questions until the coffee break. After the break, we will have an intervention, a short presentation from Aiming that should interest a lot of PhD students about opportunity with creating network with industries. Okay, but now it's questions, and after the coffee break, the presentation of Christian will continue. Okay, so some question? Okay, I'm going to run all the amphitheater.
Thanks for the talk. I just want to ask for the one-by-one convolutions. So you mentioned that if the filter, the size of the filter, if it's lower than the feature, so then it reduces the dimensions. So using one-by-one, it kind of offers dimensionality reduction. So this filter size, is it just a computation overhead, or does it affect the learning capabilities as well?
It's not the filter size, it's the number of filters.
Yeah.
Right. What do you mean? Does it reduce? It actually reduces computation because it's, I mean, a one-by-one convolution is a very simple operation. You just, it's basically a dot product between two vectors, right?
Yeah.
Okay, and you do that at every pixel. Okay, but the benefit of doing that is that the following steps, so once we've reduced the number of features, then the true convolutions, so the convolutions that are bigger, let's say 3 by 3, 5 by 5, will actually be much, much faster.
Yeah, but for example, if I have one-by-one, for example, my depth is 7, so I'm working on 7 slices, for example, and then if I choose 7 filters or 16 filters, so does it hamper the learning capabilities? I mean, for 7 slices, the computation overhead is not really significant, so I can manage. But apart from that, does it affect the learning? What do you think?
No, well, I mean, it's possible that you are reducing too much information, but in fact, if you look at very, very recent architectures like Squeeze and Excite Net, that's their whole, I mean, that's the whole concept, and they've completely shattered the state of art. So there is a sense of reducing this information, like squeezing the information, that benefits the subsequent operations in a network.
Thank you. Is it all mostly clear? There is another question after I...
Thanks. Your explanations of dropout, the first explanation kind of assumed that the network knows that there's going to be dropout so that it doesn't overly concentrate its efforts on a node that's going to drop out, which it doesn't. And the second explanation with regard to ensemble learning, it's quite different to have one network that's changing over time to multiple networks that are concurrently learning. And then, so is it fair to say the dropout's really just a way of giving it a bit of a kick so it doesn't do so well? And does that differ, for example, from stopping it earlier from over specializing?
Sure. I mean, like my explanation, especially for the ensemble, was a bit. I mean, it's a bit of an exaggeration, but there's actually like a paper that analyzed what dropout does from a Gaussian process point of view, and it sort of showed that what you're learning is the distribution of the loss over different possible networks. Okay, so it's not exactly like ensemble learning, but it is kind of related. Now, with respect to the second part of the question, it is a regularization technique. Okay, so like early stopping, or if you do weight, if you penalize your weights, let's say using L2 norm. But the thing about dropout is that it's more adaptive. So it's done during the training. Okay, it's done at every iteration, at every gradient step. Whereas early stopping is more global. It's just a way of saying, well, I've reached my optimal complexity. If I go on in the training, then I'll just overfit. So both techniques are complementary, and you can actually use them together, right? But they work in different ways.
It's me.
Yeah.
So it's about dilated convolution. Should it be used in the first layers to learn global features, and then we move back to classic convolution, or should it be dilated convolution the whole model? So just.
That's a good question. There's something that's called context module that you can take a look at. Context modules, and they actually, what they do is they actually do subsequent dilated convolutions, but what they do is they increase the dilation factor. Okay, so they basically doing maybe less dilation in the first layers, and then more dilation as you go on in your network.
Okay. I have many questions also. Okay. Just before, is there Ozan Octet is here or not? No, not yet. Okay, perfect. Thanks.
This may be a pretty basic question. What's wrong with just using a linear activation function? Why do we need to rectify it?
It's a very, very good question. So I think Pierre-Marc answered that question in his talk. The fact that imagine you have a network where you only have convolutions and linear activation, I mean, fully linear, then you will only have your network will only have the ability to learn a linear function, right? Because the convolution is a linear function, and then you can show that a linear function over a linear function over a linear function, etc., is itself a linear function. So in the end, your network will just be a plane, right? Which is not very interesting.
Okay. One more? Okay.
Hello, sir. I have some confused some words about. I heard some deconvolutional and upconvolutional, and you said transposed convolutional, and some other words like upsampling and upsampling with learning. So I'm a little confused about these differences.
Right, it's very confusing. Sometimes in the literature you will hear the word deconvolution, okay, which is actually not a correct word. The correct word is transposed convolution, okay. It's a type of unsampling, but it's not like interpolation in a sense. It's a type of upsampling, but it's not like interpolation in the sense that you're not just you're not just taking the information and sampling it to higher resolution, but you're actually learning. So there's actually some parameters. Let me go back. There's actually some parameters here that tell you how you upsample. Okay, in fact, the upsampling that you will compute might look very different from what you would have had using simple interpolation, for example. Okay, so it's upsampling in the sense that we will generate a higher resolution image, but it has nothing to do with interpolation.
Okay.
To continue on this question, I mean, there are many different upsampling schemes with very various weights. So, in my point of view, this is not very different from interpolation, actually. But what I do believe is that the skip connections make it different from interpolation, actually.
No, I disagree with that, because if you look at the encoder-decoder architecture, okay, where you only have convolution pooling, and then you have upsampling, or transpose convolution, there's no skip connections here at all. Okay, this is a very naive architecture in the sense that nobody really uses that anymore, because we know the benefit of skip connection. But it's also very different from what you would get if the upsampling was just interpolation. Okay, if you had interpolation, I'm not sure what you would get, but probably some very blurry kind of version of your. You would get a blurry version of this, whereas if you use transpose convolution as upsampling technique, you can actually recover very nice edges, like what you see here. Right? If you look here, this is not blurry at all. This is a very sharp segmentation mask.
Because it's non-linear. Okay.
Right, because it's not linear, yeah.
But still for interpolation. It doesn't have to be linear to be interpolation.
Right, it's a form of interpolation. Yeah, you're right. It's a weighted sum of your low-res image, so it's a type of, in the same way that a convolution here is a filter, right, like an image filter.
Okay. So I have one question. You present the batch normalization also, but I know also there is a kind of discussion for where batch normalization should be placed according to the neuron and the activation function.
You do it. I think you do it after the activation function.
After the activation?
Yeah.
Ah, okay. Okay. I was thinking because after the activation function, also you have maybe one redundance with the bias and the beta parameters. It's almost the same.
Yeah.
Okay, and is not troubling the way of working of the network.
No, because this parameter is learned anyways, right?
Yeah, one more.
So you can do it before or after.
Yeah, one more is not okay, not critical. Okay, other questions? I insist about it because I know what hands-on sessions are coming, and I know that you will need it. Maybe, yes, one more question about dropout also. Can you explain when dropout is again randomly selected? When we select the neuron that will be in fact completely cancelled, is it at each iteration or at each epoch, or what are the commonly way of usage of such things?
I think it's at each iteration, but it's only during training.
Of course, yeah.
Of course, yeah. So you
at each iteration.
Yeah.
Okay. Thanks. One more question? Okay.
It may not be related to what you've presented today. What is reinforcement learning?
Oh, okay. So reinforcement learning is, yeah, the best way to describe this with an example. Let's say you want to teach a car to drive itself, right? And basically driving a car is turning the wheel, pressing on the gas and all that, right? In a standard supervised learning way, you would, let's say the car would see an image, right, from the camera, and then you would tell it exactly for this image, you have to turn the steering wheel exactly like this, press on the pedal exactly like this. This is the standard supervised learning. As you can imagine, this is impossible to do. I mean, it was very, very complex. Whereas reinforcement learning, you say, okay, I'm not telling you exactly what you should do, but I'm going to give you a reward instead. Figure out how to drive, and then I will give you a reward if you're doing good, or no reward if you're doing bad. So a reward is actually more simple to encode. It could be driving off the road, following the lane, etc., right? So it's a very different learning paradigm. Yeah.
Okay, more questions? Yes, I still have some, so be careful. Other questions? Okay, for me, okay, no problem. When we discuss about very deep neural networks, as the Google Net, I'm still have some trouble understanding how the different losses functions and the gradients coming back are merged, because they can be in opposite sense. Is there some point of view? Is there some techniques to merge such things as in the Google Net?
So, for example, here.
Yeah, exactly. At some layers, we are going to meet many gradient information. Can you explain how it's possible to do it and what are the classical techniques?
Oh, it's just a sum, right? You have to sum, basically when you compute the gradient, I mean, this is the chain rule, you have to sum the gradient from all the edges that go out of this node, right?
Okay, so simply sum the different gradients
Yes.
coming from the different canals.
Yep.
Okay.
The simple sum.
Very simply.
Yep.
Thanks. Just a general intuitive sort of question. Yesterday it was kind of explained how the basic network was doing conditional probabilities.
Yeah.
Once you do all this, do you think that there's any relationship left at all with posterior probabilities? You know, it was said that someone famous answered the question, "Why is it so good?" And said because it's good at conditional probabilities, posterior probabilities.
I mean, there are some works that have tried to connect, try to make the networks we're like in a Bayesian sense, but. I mean, it's just an intuition in a sense that there's really no connection. We're trying to learn a distribution. This is what we're doing, right? So it sort of makes sense to call it a probability, but it's not. There's no guarantee that it's a real probability. They're just values that sum to 1, basically.
Just about pooling, I'm asking how can achieve rotation invariance using pooling?
Right. Okay. Well, that's a very good question. I think it was also answered a bit by Pierre-Marc. So the idea is that if you take the maximum value, right? Let's say you have an image with a bright pixel. Okay. If you shift that image or that object with the bright pixel in the center, as long as you don't shift it. As long as the shift is within that max pooling window, the response will be the same, because that pixel will still have the max value.
But this is a shift invariance.
Yeah.
We're talking about rotation invariance.
Rotation invariance, well, for small rotations, it's the same principle, right? Right.
Just for small rotation.
We're talking about very, very small shifts and small rotation. It will, of course, if you completely flip the image, then max pooling will not have any effect on that. Okay, so let us continue where we left off. We stopped at the presentation of segmentation. Now we will see a different problem of also great importance. It's object detection, right? So compared to classification, so in classification we have an image, we want to find a class. Here we want to find a class for each object, but more importantly we also want to find a location of these objects, okay? And the location is given typically by a bounding box. So I'm going to present to you three very popular architectures, but it's mostly some architectures that were improved. So you had a first architecture which was improved by the second one and the third, right? So the first architecture is called region CNN, or RCNN, and it works as follows. Okay, so the first step is to extract what we call region proposals. This can be done using pre-existing algorithm, and that will basically generate a lot of bounding boxes in the image that might contain objects of interest. Okay, so step number 2, we will, for each of these proposals, we will wrap the region into a fixed size image. Step number 3, we will pass these warped proposal images to the CNN to compute features. And then we will use these features to do two things. One is classification, so what is the object, if any, inside the region or the image. And 2, we will compute, we will do a regression to compute some offset on the box. So there's two things that we want to compute. One is the offset of the center, okay, because it might be a little bit shifted. And 2 is the offset of the scale, so the width and the height. Okay, and then because we might have a lot of detected regions, some of these regions might be overlapping, we will do what is called non-maxima suppression to remove the redundant detections. Okay, so that was the first main network that was proposed for region, for object detection. That was really popular, but there was some big issues with that. The main issue is that it was very, very slow because there was many stages. We had to do region proposal, we had to compute convolution features for each of these proposals, and then as a third step, we had to do the classification and the bounding box regression. Okay, so let's see how we can take this very simple idea and make it better and better. So the first improvement, first major improvement, I should say, came as a network called Fast RCNN. And the idea is very simple. So instead of computing convolution features for all the different region proposals, why don't we compute the convolution features only once in the beginning over the whole image, and then do the pooling over these features for all the different regions, the different proposals. Okay? So that saves a lot of time because the convolution features are computed only once, even though we may have thousands of proposals. Okay, but again, it's still not perfect because we still have to generate the proposals in a different step, okay, using a different algorithm, etc., right? So what is the next step? Obviously, we want to have an end-to-end solution, right? We want to do the proposal within the network. And this is exactly what faster RCNN does. Okay? So again, we have an image, right? We compute the convolution features using your favorite convolution network. And then we do two things. The first thing is we compute some region proposals. And how do we do that, right? Because there's an infinite number of proposals. Well, this is done in a very clever way. So the way that it's made is that there are some predefined regions called anchors. Okay, each anchor has a different shape. Okay, you could have small boxes, elongated boxes, boxes that are, square and large, etc., right? So we're going to compute, for each of these anchors, we're going to compute basically the bounding box regression and class. Okay, so we have different hypotheses. We do a prediction for each of these hypotheses, and then in the end, we keep only those, using the same technique, only those that are the most relevant. Okay, again, I like to show you some examples of how this can be applied to medical imaging. There was some very nice examples shown, I think it was on Monday, no, it might have been yesterday, where they were showing the detection of polyps during a colonoscopy. So this example here is for detecting pulmonary nodules. And then if you take segmentation and you take object detections, obviously you can combine both and do what we call instant segmentation. Okay? So in instant segmentation, we want to detect individual objects, but we also want to segment them. Okay? What is the main difference with segmentation, right? So if I gave the same image that's on the left, and I asked the segmentation algorithm to come up with segmentation mask, how would the result be different with what I get here? Does anybody know? Pierre-Marc, I'm sure you know. Okay, segmentation basically maps every pixel to a category, right? So what would have happened is that both cats would have been mapped to cat, right? We would have both cats combined into the segmentation of cats. But this is not what we want. We want to segment the two different cats and recognize that they are different cats. Okay, I'm not going to go into details, but basically how this is done, I mean, the architecture is very simple to those that I showed before. The only difference is that we have an additional branch which will compute for every proposal a segmentation mask. Okay, so basically we have different proposals. Think of them as the anchors that we saw. And then for each of them, we will compute a segmentation mask for every possible class. Okay, so we're doing a lot of work here. Okay, so imagine there's an image, there's a proposal here, then try to segment this to find cats, try to segment this to find dogs, try to segment this to find all the different possible class. Okay? The main principle here is that we make the segmentation independent from the classification and the bounding box regression. And once this is done, we use the classification to decide which of the masks we should keep in the end. Okay? So it's like we're doing multiple segmentation hypotheses, and in the end, we pick the one that is most consistent with the class that we detected. Yes?
In this case, is there any limitation about the number of objects you're going to find inside the network? Do you put any constraints about this number, or you let the network decide?
There's no constraint.
Okay, so if you put an image with a lot of objects, you're going to find all the objects in the image.
Yeah, possibly. Yeah, possibly. But there are limitations in the sense that there's a limited number of anchor boxes. When you do the non-maximum suppression, you might, eliminate if two, let's say two people are very close to one another. It's possible that you might merge them together. Of course, it's not perfect, but technically, in theory, you should be able to detect all the objects in an image, yeah, and segment them as well. Okay, so here's an example for tissue lesion detection and segmentation. It might be hard to see, but right, not only are we detecting the lesion, but we're also segmenting it. Okay, I will move on quickly to different topics, and if I run out of time, it's okay because all these topics are independent and the slides will be available online if you are more interested. Okay, so a big problem with dealing with images is the spatial invariance, right? So the same object could be anywhere in the image, could be rotated, scale, etc. And a very common strategy to deal with that is doing data augmentation, right? So data augmentation, we take our training images and we make modified versions of them by scaling, rotation, translation, and we feed those as additional training images, okay? The question is there a better way of doing this? Can we do things a little bit smarter? And one approach to do this is called spatial transform. So the idea is, instead of assuming that the image can be transformed in any way, and doing this before, so doing these augmented data sets before training, why don't we try to learn within the network the normalization itself? So that regardless of the image that we get, the network will learn to normalize it, to remove this kind of shifting, translation, rotation, and give it to the form that it needs to make the computation. So how does it work? So we will use a localization net to compute some transformation parameters. Okay, for example, if it's a affine transformation, there will be some translation, rotation, scaling. Then we have a predefined grid that will be warped using this transformation. And then we will simply project the image onto this transform grid using sampling. Okay? So again, the cool thing about this is that this is fully learned. Okay? We don't have to make any assumptions about the transformations that we will encounter in our data. In theory, the network can learn by itself to remove this spatial variance. Another really, I think, cool topic, and I think some of this will be seen in the talks that we will have during the week, is autoencoder. Okay? So if you remember the encoder-decoder network that we saw, this is exactly the same idea, except that we want to decode the image itself. So we have an image, we encode it, and then we want to recover the image. So why do we want to do this? Well, for the same reason that we do PCA. Okay? We want to learn a low-dimensional representation, which is called the encoding of our image. Okay? And then what we can do with this representation is that we can just if you think of this as a manifold, like a low-dimensional space, hopefully if we move into that manifold, well, we can generate slightly different images that could be useful for many things. If I think of GANs, GANs are based on this principle. Okay. There is a problem of doing this, which is that here I show the manifold space, so the 2D projection space of digits. And there's a problem is that if I assume that my space is uniform and I go from one point to the other, because there are a lot of gaps in that space, what I might get in between these two well-defined points could be anything. It could be something that doesn't look like a digit at all, okay? And when you work with generative models like GANs, this is just terrible, okay? You really want to have a very dense and uniform space that you can generate coherent samples wherever you move. So one very cool way of doing this is what we call the variational autoencoder. And the idea is this. So instead of computing for each image a mapping in a low-dimensional space, what we will compute is a distribution. Okay? So the distribution is basically given by some parameters. If you think of a Gaussian distribution, you have the mean and the variance. And then what we do is that we do a sampling over that distribution, and we want to make sure that we want to minimize the reconstruction loss for each of these samples. Okay? So instead of saying, I want that specific point to reconstruct well a given image, let's say it's a cat, what I say is that I want this point to reconstruct cats, but I also want all the points within the neighborhood, so as defined by my Gaussian distribution, to also reconstruct cats. Okay? And if I do that, then my space becomes much more regular. Okay? And on top of that, what I want is, I want this distribution to be centered at the origin, so zero-centered, and have a variance of 1, right? Because if I do that, then I know that my manifold will have more or less Gaussian shape. And then if I go from this point to that point, I'm very likely to encounter something that will look like a cat or any of the objects that I'm encoding, okay? So this is a bit of an advanced topic. I'm going really, really fast here, but what I really want you to get here is the intuition. Why are we doing this, and how does it work? Okay, what can we do with this? Well, we're seeing a lot of applications of this in medical image, maybe starting about 2 years ago. One of the really cool applications of this is what is the probabilistic U-net, which was proposed at CVPR 2000. Wait, what am I saying? Was it CVPR? NIPS. Yeah, it was NIPS last year. Yeah, NIPS last year in Montreal. And what's really cool here is that because now we have a distribution of our encoding, we can generate multiple segmentation hypotheses, okay? And this is really cool because before, you have an image, okay? You give it to the network and the network gives you a segmentation, okay? Maybe the network is doing a good job, but maybe it's not doing a good job. So what do? You have no, if the segmentation is not what you like, there's nothing that you can do. You have to take it and that's it. With probabilistic U-net, what's interesting is that it can generate multiple segmentation hypotheses and can say, well, this is the segmentation, but this could also be a segmentation, or this, or this, or this, in the same way that if you ask different experts to segment an image, they might come up with different results, okay? So there's a lot of really cool things that we can do with this, and hopefully we will see some nice applications in the near future. So another thing that I've personally been working on is graph convolution. Okay, so basically taking the concept of convolution beyond standard images. Just to give you a motivating example, think of learning on a complex surface like the cortex. Okay? If you look at the image, like a zoomed image of a cortex, if you look at points A and B, in the image, they are very close to each other, I mean, almost neighbors, but on the surface itself, these points are not neighbors. Okay, so if you apply like a standard image convolution, you will completely lose that, that information that the points are actually on a complex surface and they're not, they might appear to be close to one another, but they're not. So what is the solution? Well, instead we can model the image or the information as a mesh. Okay, the mesh is a graph, and then do the learning on this mesh. So I'm gonna go really quickly over this. It's sort of technical. I just want to show you two main ideas of doing this, two main ways of doing this. The first approach uses what we call the Laplacian Matrix. I think it was introduced on the first day when the talk about unsupervised learning. Okay. So the Laplacian basically encodes the connectivity of your graph. It's not the adjacency matrix, but it's related. And then if you take the eigendecomposition of this Laplacian matrix, right, you can write what we call a spectral graph convolution as this. Okay, so U is the eigenvectors of your matrix, and X would be the features computed at every node of your graph. Okay, and U transpose X is what we call the spectral, the graph Fourier transform. What is this? I mean, okay, this is a nice mathematical equation, but what Intuitively, what is going on here? Well, basically, the Laplace matrix is kind of like an operation that diffuses information, okay? So what's going to happen is that the information at one node, okay, is going to be diffused within the network to other nodes through the connectivity, through the edges, okay? And this is done by the eigen components of the Laplace matrix. Another technique for doing convolution on graph is what we call geometric convolution, okay? And this has a very intuitive interpretation. One way of seeing a convolution, a standard convolution, is think of it as basically some impulses that we apply on a grid. Okay, right? So this is a convolution. Let's say we compute the convolution at this pixel, right? So we will take the value here, so we can think of it as the response of this Dirac delta, if you want, of this peak at this position, plus the response at this position, this position, this position, this position, etc. Right? Okay, so if you're familiar with signal processing, I mean, this should be fairly obvious to you. Okay, now, so how do we extend this to something that's not a regular grid? So what if my pixels could be anywhere in space, right? Okay, that's a bit more complicated, but it turns out that it's not so hard to do, okay? What we can do is, instead of having these unit responses, like these very peaked distribution, we can use for example, some Gaussian kernels, okay? And then what we can do is, like, the convolution at this point is the sum over all the neighbors, and for each of the neighbors, the sum of the responses for these Gaussians. I mean, it's exactly the same as this, except now these distributions, these peaks, can be anywhere in space, and they can have various shapes.
Christian, sorry, I think if you can finish your talk in a few minutes, it would be great, so we can continue after that.
Okay, no problem. I have only maybe 2 slides left, so it should be
perfect. Thank you
good.
so much.
Okay. Okay, so we use this for cortical surface parcellation. So think of it as segmentation of a surface. Okay, with very good results, in fact. But you can also use a similar idea for classification, right? The only trick, the only challenge to go from there to classification is you need to figure out pooling, and pooling on a graph is very tricky, okay? Because you cannot say, this is my region, I will do max pooling. Now, you know, what is the region on a graph, right? So you sort of have to start including concepts of clustering. Okay, to finish off, I think I have only 2 slides on recurrent neural nets. I mean, very, very quickly. So when you do, let's say you are reading a book, okay? When you read a sentence, when you're trying to understand that sentence, you basically remember what you have read in the past, of course. You know, it doesn't make sense to, how can you interpret a sentence if you don't know the context, okay? So this is what recurrent neural nets are trying to do, okay? So every prediction, okay, will depend on the predictions made in the past, okay? And another major advantage of recurrent neural nets is that it can be applied to sequences of any length, okay? So we're not limited to fixed size images. We can have, for example, sequences of 10 elements, 20 elements, okay, like that. There is however, in this very simple idea where we just unroll, if you want, a network, we make multiple copies of the network and we say the output of the network is fed, or the state of a network is fed to the next copy of the network, etc. The problem is that it has issues learning long-term dependencies. Okay, it tends to forget the things that it has seen a long time ago. Okay, just like how a Markov network will only consider the previous step. Well, this is not exactly the case, but there's a similar effect going on here. So one architecture that was proposed a long time ago to solve this problem is called the long short-term memory network. So, I mean, if I show you this, you probably have no idea what's going on. I'm going to break this down into 3 things to make it easier to understand. So it does 3 things. So this is the input at time t, okay? And what you have on top, so this is what's observed at time t. This is the output of the previous time, and this is the memory. Okay, so there's an effect of a memory. So the first thing that we need to determine, or I mean what the LSTM has to determine, is what to forget. Okay, we don't want to remember every single thing we see in the past, because at some point that's not going to be useful. Okay, so there are some things that we might want to forget. Then the second thing is, what do we remember? In the sense that there are some computations that I'm making now. Which of these computations do I want to add to the memory such that future computations will benefit from this information? Okay? So it's imagine you have a memory. What do you erase? And then what do you add to the memory? And lastly, what do I output? Okay? And, okay, so LSTMs, okay, CNNs I understand is for image, LSTM, recurrent, it's usually used for text. Why are we talking about this? Well, there's many ways that we can use LSTMs, for example, when you have temporal images, but one really cool application of this is that we can start to combine images with text, okay? And okay, where do we have, in what situation do we have text? Well, for example, clinical reports. Okay, there's 2 things that we can do. Either we can use medical reports to help the prediction, so for example, to help the segmentation or the classification, or even more interestingly, I mean, if you think very far in the future, and I mean, we're almost there, is that maybe we can use the images to generate reports. Imagine how that cool would be. Okay, we feed an image to the network, and then the network will generate a report that doctors, radiologists can read through and say, okay, well, this is what you've seen in the image. This is what you've detected. You're showing me that it's there, but I don't have to necessarily go through all the image. I can just read your report. Okay, so the way to do this basically is to have a convolution network which will process the image and compute features, and then use the features from the convolution network in conjunction with LSTM to generate sentences. Okay, with that, this is the end of my talk. So if you have any questions.
Thank you so much, Christian. I think we can really thank you so much for this very nice talk.